Now let us see what will happen in compression when you start increasing your grade of concrete. So you see here three curves I have plotted. This is only we are looking at compression, okay, not tension. And you can see that concrete contribution in tension is only valid up to it reaches its tensile strength. After that, the concrete cannot really contribute. Only steel is doing all the work. So that is why the role of concrete in compression is more important, and role of steel in pure tension behavior is more important. Okay, so you can see here with the increase in your grade of concrete. So as you go from 15 to 25 to 35, you can clearly see here that the compression capacity is going up, and you can also see the slope. Okay, the slope is also increasing. That means the stiffness in compression is going to increase if you increase the strength of the concrete. And but there is no really big change if you look at it, because for up to 40 megapascal concrete, we know that as per the parabolic model, all of them are going to reach its peak strength at a strain of about 0.002. So that is why if you look at it, the strain corresponding to peak is not really a big change. Okay, all of them are reaching its peak load capacity at the same strain or same deformation level, so there is no change. And but what is important is the load capacity proportionately increasing with respect to the increase in strength of concrete. So if you want to increase your pure compression capacity in a column, the best thing to do is to put higher grade of concrete that will give you a good improvement in stiffness as well as good improvement in strength. In fact, that is what people do it in multi-story building. When you go for taller buildings, the ground floor columns or the lower story columns will have high strength. As you go upper stories, the grade of concrete can be reduced to reduce the cost of construction. Okay, so as the appearance is increasing, the stiffness is increasing and the axial capacity is increasing. However, the role of concrete in tension is not going to be very significant, and it's only the steel that is going to play the major role. Now that is what we are saying. What is the effect of percentage of reinforcement on tension? So now here I've kept the compressive strength constant. If I start increasing, we have taken in the previous example 4 numbers of 25 mm dia. If I increase it to 8 numbers of 25 mm dia or 12 numbers of 25, that means basically I'm doubling and tripling the amount of steel. You see here again, there's going to be a slight improvement in your cracking capacity. But more important is right after cracking, the stiffness is going to be pretty high. Okay, so here this is for actually 12 numbers. So this is 12 numbers of 25 mm die. So that what we have considered. Okay, so more the amount of steel that I'm putting in tension, it is going to give me higher post cracking stiffness. But it is going to be minor change in your cracking load, not major. But if you look at the yielding capacity also is going to increase. So we have taken the elastic perfectly plastic behavior for steel. That is why this is also resembling like that. But if you look at it, the yield deformation is also, there is no change. However, the yielding load capacity increases in proportion to your amount of steel, because that is directly coming from your equilibrium equation. It's basically AST multiplied by Fy is your tension capacity of concrete prism in tension. Because when steel is reaching yielding, concrete would have cracked completely and it will not offer any load resistance. It's all the work is done by only steel. So that is why you get very high amount of load capacity with increasing amount of steel. So as the AST is increasing, in tension, it is increasing your stiffness, it is increasing your axial capacity in tension. But however, cracking load, there will not be any change, because the percentage of steel itself, what we are dealing with, is in the order of 2 or 3 or 4% maximum. So when you do that at a very slow strain, when concrete is cracking, we have seen that concrete is cracking for 35 megapascal at 0.000117. It's a very, very small strain. So the amount of stress that is you're going to get from steel is going to be very less. So that's why the cracking load is not going to be any different. Okay, so this is the effect of reinforcement on the tension behavior. Okay, So now let's briefly discuss. We'll do this one more example. We'll solve what is the load resistance for some certain strain levels, like what we have done in the previous parts. Now what we are doing is, instead of dealing with the low strength concrete, if we change it to high strength concrete like 60 megapascal or 80 megapascal, how the behavior is going to be. So I'm keeping the same cross sections, 250 mm by 250 mm. I'm keeping the same number of steel, which is 4 numbers of 25 mm diameter. Length of the member is also 1 meter or 1000 millimeter, like what we have done in the previous examples. Now only the grade of concrete is not less than 40. Now it's 60 megapascal. As you know that parabolic model or Hognestad strain curve model what we have adopted, it is valid only for concrete strength up to 40 megapascal. So now when I'm using a 60 megapascal, I cannot really use a Hognestad strain curve model because it was not intended for high strength concrete. So we have seen it in the material chapter to uh, to capture the strain curve behavior. Thorenfeld did a lot of experiment, and the Thorenfeld model is widely adopted for predicting the behavior of high strength concrete in compression. So that is what we have taught up. So now we have discussed previously also, right? So this is the difference between normal strength concrete and high strength concrete. As the strength of the concrete increases, we have seen that epsilon prime C is going to keep increasing. However, epsilon Cu, the failure strain. So there is a difference between epsilon prime C and epsilon Cu. Epsilon prime C is the strain corresponding to the peak strength of the concrete. However, epsilon Cu is the failure strain of concrete. The failure strain of concrete, the difference between epsilon Cu and epsilon prime C, we have seen that, or in other words, the post-peak ductility is going to keep reducing as you increase in strength of concrete. That is reflected by the steep drop in this stress at strains higher than epsilon prime 6. So this is the behavior. So this we have to take into account because this is not reflected in your Hognestad model, the steep drop. Okay, so that is why the Thorenfeld developed this relationship. So again, for any strain epsilon c, we should be able to predict the stress fc, and f prime c is usually given to you because we can test. We can do a load control test and quickly find out when we do the mix design what is going to be your average cylinder strength, right? And epsilon prime C also will be given to you. And if I am able to get the values for N and K, then we can find out for any given values of epsilon C what is stress. So now what is N? N is a factor that is accounting for how the curve is changing from elastic to inelastic behavior. Okay, so for example, when you look at it as red color behavior, initially it's all straight. However, after a certain point of time, it is going to change. Okay, or in other words, from up to 40% of your stress, usually we take them behavior assumed to be linear elastic is reasonably a good prediction. From 40 to 100% of your strength, how the shape of the curve is going to change will be accounted by a factor called N factor. How the curve changes from linear to nonlinear behavior in the pre-peak regime. Okay, and there is another factor, K factor, which we discussed in the material chapter, that accounts for post-peak decay in strength. How fast the strength is decaying after reaching the peak stress. So if I are able to get this N and K value and epsilon prime C and F prime C, then using this equation, we should be able to predict for any epsilon C what is Fc. Because to predict your axial behavior for any strain, first we need to find what are the stresses in the concrete and stresses in the steel. Though strain in the concrete and strain in the steel is going to be same, but their respective constitutive equation or constitutive behavior is going to be different. So that is what we need to account for. So again, like what we did in the previous um, examples, again we are going to choose different strains, 0.001 like this, and then the area of only concrete, as you know, we keep the scale is same, so it is going to be 62,500 minus 1964. So only concrete area is 60,536, and area of steel is 4 into 491, which is 1964. And concrete, as we have seen, we have to take it from Thorenfeld's model, and we are looking at now pure compression. That means we are looking at compressive strains. Okay. So the elastic modulus again is given by this equation, which is already we have described this in the materials chapter. If you want, you can go ahead and look at it. Now here also we can see that we have taken strength of 60 megapascal. So this is an equation where it is written in terms of cube strength. Okay. So that is why I am taking 75 here. 60 multiplied by 1.25 is 75. Okay. So that is what we are taking, because this in this equation the cube strength is incorporated. So the cylinder strength is given as 60 megapascal, and cube strength has to be converted into as 60 multiplied by 1.25. So then you got, then n is a value that we have discussed how the curve is changing from linear to nonlinear behavior in the pre-peak regime. Again, people have done a lot of experiment and empirical equations have been developed. So that is again function of your cube strength, and this is a constant. So for this grade of concrete, what you have taken, n works out to be 4.33. Similarly, epsilon prime C is also, which we have seen it for 60 megapascal, it works out to be 0.002 as per this EC that what we have calculated. And so you can see 60 is your F prime C, and this is your EC, and this is n divided by n minus 1. So that works out to be very close to that of 0.002. And in fact, as the strength of the grade is increasing, you are expected to have some increase in epsilon prime C. But for this grade, that what we considered 60 is not very high strength. So that is why the epsilon prime C has not really changed much. Okay. And K is going to be for the pre-peak regime, when epsilon C value that what we are considering, when it is less than epsilon prime C, K I have to take that as 1. When epsilon C goes higher than epsilon prime C, then I have to find out the values for K. So for example, in this case, I am taking epsilon C equal to 0.001. Now, so 0.001 is lesser than 0.002, which is epsilon prime C. So that is why K value will remain same, 1. And you know the Thorenfels equation. So if we go back and put this, right? So now I got n, I got k, I got epsilon prime c, and f prime c is given as 60. So I can find out what is fc. So that is what we have done. And for this strain of epsilon c equal to 0.001, I got a value of 38.44 megapascal. Now that we got the stress in the concrete and the stress in the steel, we know that when epsilon s, because epsilon c is equal to epsilon s, because there is strain compatibility. And epsilon s, if it is 0.001, which is less than the yield strain of 0.0025, so the stress in the steel can be directly calculated by strain multiplied by elastic modulus. So then it works out to be 200 megapascal. Now I got both stress in concrete and stress in steel. I can put it in your equilibrium equation. I got a value of 2720 kilometer approximately, right? So you keep continuing this exercise. So we choose the next value of strain, which is 0.002. I'm going now high. Now, what is your peak strain? Epsilon prime C is 0.002. So we are exactly reaching 0.002. So you should get a value of stress equal to 60, because it should reach at a peak strain of 0.002. That is the value that you're choosing. And epsilon prime C also, from a previous calculation, we got that to be 0.002. So when epsilon C reaches epsilon prime C, it should reach the value of F prime C. So if you plug in back, then you got your 60 megapascal. This is important because the concrete is going to reach maximum stress at peak strain. And in compression, that is the strain at which you are going to get maximum load resistance. So that is why we are doing the calculation at this strain, which is 0.002. Now the steel stress again, still 0.002 is less than 0.0025 for the grade of steel what we are considering, which is 500 megapascal. Again, what is the yield strain for 500 megapascal? 500 divided by 2 into 10 to the power of 5 megapascal. So if you do that, you will work out to be 0.0025. Okay. Now the strain what we have considered is less than 0.0025. So stress is directly multiplied from elastic modulus as 400 megapascal. So again, we put it in the equilibrium equations, and you got a load of 4,417 or 18 kilonewton. Okay. So similarly, we can do the calculation for other strain also. And when the value becomes, again, if you see here, as we have done previously, it works out to be very, very concrete. At this thing, concrete will reach, only steel will contribute. That is why the load resistance did not change compared to that of 40 megapascal. There also concrete contribution is 0. Here also concrete contribution is 0, because for high strength concrete, you know that failure strength will be lesser than that of what you get for 40 megapascal or 35 megapascal concrete. So that is why you see here the load is increasing and then it is going to drop. Okay. So in this way, we can do the calculations for compression, right? And then now we'll see what happens for this high strength concrete under tension. And now you can see, why did I select this value of 0.000153? Again, this corresponds to cracking strain. So now how do I get my cracking strain? So we have taken again 10% of compressive strength as my tensile strength. So for this concrete, tensile strength is going to be 6 megapascal. If I know the elastic modulus, 6 megapascal divided by elastic modulus will give me what is the strain at which it is going to crack. So that is how we got this point triple zero 153. Now you can again go back. What is the EC that we got previously? If you go back to this EC, we got to be 39,202 megapascal. That's not going to change. That is elastic modulus of concrete in compression, right? As per this empirical equation, just like what we have done 5,000 square root of FCK. This is the EC, that is the value that is such a, again experimentally calibrated for Thorenfeld's equation. So once you got your EC, then you can get again 39,200 multiplied by this strength will give me my tensile strength at which it is going to crack, which is equivalent to 6 megapascal. This is also why we are doing it specifically at this point. At this point, I'm going to have cracking. Okay. So again, if you look at it, for this strain, the steel is going to offer a very low amount of stress. You see, the grade of steel what we are dealing with 500 megapascal, but a strain of 0.000153, it is giving you only 30.6 megapascal. It is not even offering 10% of its yield levels. Okay, so it's about 8 percentage or so. Right, it's a very, very low stress it is offered by steel, because the strain at which it's going to concrete is going to crack is going to be low. That is why the steel will not really play a major role in cracking load. Okay, it may slightly marginally increase depending upon the amount of steel, but it's not going to make a big difference. So again, when you substitute these values, now you are looking everything in tension. Okay, so this will also be in tension, this will also be in tension. Now everything is there, so that is why you get a load of negative 423 kilonewton in tension. Okay, when the concrete is cracking. So you go back to the RC, that what you done, we got about 257 or so. Here we got a 423. Why? Because the tensile strength of concrete is also increased. When I increase the compressive strength of concrete, automatically tensile strength of the concrete is also increasing. So that is why we are finding increase in your cracking load. So this is your cracking load for high strength concrete, which is 60 megapascal concrete. And again, we keep continuing this the exercise. Okay, we keep increasing the strain. Now I'm choosing a value of 0.0025, like what we have done previously. Why is it? At this strain, the rebar is going to yield. So I want to see, this is the maximum the load capacity that particular concrete prism can offer. Okay, so through compatibility, again the same strain, if I'm considering steel also going to have same strain. However, concrete now it is cracked. Okay, so at a strain of 0.0025, concrete is completely cracked. It is not going to offer any load resistance in tension. So that is why the FC value I'm taking it as 0 megapascal. Okay, so you keep continuing this exercise, and Fs becomes maximum value of yield stress corresponding to 500 megapascal. So when you substitute it, you get a value of 982 kilonewton. So please go back for when we use for 35 megapascal also, we got the same tension capacity. When we use 60 megapascal also, we are getting the same tension capacity. So what does it tell you? Concrete strength is not going to play any role in tension capacity of the concrete. Okay, so the tension capacity is only determined by the amount of steel and the grade of steel that what we are using. So that is why the 982 kilonewton is not really changing, even though I am putting high strength concrete, because even though high strength concrete, it is going to help me only in increasing the cracking load, but it is not going to play any role in maximum tension force that it can offer. Okay, so we can do the calculations like this, and then you can see that 423.3 has become 982, and then after that 982 will be remain. It will keep on offering this 982 until the bar is going to rupture or it's going to fracture. Okay, so that will happen at a very high strain levels of more than 10% or so. Okay, so now if you start comparing this behavior between M35 and M60 or 35 megapascal and 60, you can see that definitely the concrete capacity is increasing in compression when I increase the compressive strength of concrete. But if you look at it, the strain or the deformation at which it is attaining the maximum compression capacity is not really changing, because we have epsilon prime c is the strain at which it is going to reach its maximum stress. That was not really changing. So that is the reason it is in. So another thing is, with the increase in strength of concrete in compression, of course, my elastic modulus or the stiffness of the system of the member has increased as expected, because concrete is a major load contributing member in a RC member for compression. Okay, but however, when you look at it in tension, if you see here, when I use high strength concrete, of course the cracking load has increased. That's what we have seen, 400 and something we got compared to RC, which had about 250 or so. But if you look at the ultimate tension capacity, which remains at 980 kilonewton, whether you're using M35 or M60, it is not really changing. Okay, similarly, the post cracking stiffness also is not really changing. Okay, because that is purely function of the amount of steel that you're putting, but it has nothing to do with what kind of concrete that you're doing in tension. So, in summary, what we can say, if you want to improve the compression performance, you should, in pure compression, you should be very careful about your concrete properties. And steel is going to help you in little bit, but it's not really going to help you much. But in tension, only for increasing your first cracking in tension, concrete strength will help. However, for ultimate strength in tension, concrete is not going to play any role. So as the increase in strength of concrete, stiffness is increasing, compression capacity is increasing, cracking load is increasing. However, in tension capacity, absolutely there is no change, because it is purely function of the amount of steel that what we are providing. Okay, right. So in this module, what we have discussed was the basic laws of mechanics. Okay, and for any rational model or to predict the behavior, we need to follow the fundamental laws of mechanics, which is it has the member or a structure should satisfy equilibrium, and it should satisfy compatibility conditions. Okay, compatibility condition, either it can be expressed in terms of deformation or it can be expressed in terms of strains at the cross section level, and it should also follow constitutive relationship that what we have seen. So basic laws of mechanics we have discussed, and we also discussed the load displacement behavior in pure axial compression and tension, and the role of concrete and steel in compression and tension also we discussed. I think again, to improve the performance in compression, we should be very careful about the properties of concrete, because that is the major contributor. But if you want to improve the performance in tension, especially the ultimate tension capacity, we should put more amount of steel or use high grade of steel. Concrete is not really going to play a role. However, concrete will help you in increasing the first cracking load and tension. Okay, so again, the behavior of normal and high strength concrete under axial loads, we have explained the differences, right? So with this, we are completing this module, right? Thank you for your attending this lecture, and we will see you soon in the next module. Thank you.